All right, so our first example says, for the function f of x equals x squared minus 1, all raised to the power 3, determine the intercepts, critical points, intervals of increase and decrease, and then graph the function. Because of your prior knowledge, functions, and in this class, we do know a lot of information already about this function. We know that it is degree 6. Again, we have something x squared raised to the power 3. We know that it has a positive leading coefficient, and since it's degree 6, it's an even function, which tells us that it goes from quad 2 to quad 1. Now, I don't necessarily need you to write this out, but it is a good idea, just so that as you're working through this question, you can make sure that everything that you're getting makes sense for what we know about this function. So the first thing that I'm going to do is start off by finding my intercepts, and it is a good idea to just label what you're trying to find. I can't write apparently. What is going on here? There we go. It definitely will help you stay organized, and it's going to help me as I'm marking your questions. So first I'm going to find the y-intercept. It doesn't matter what order you do this in, and to do that I'm going to make x 0. So when I do that, I get f of 0 is equal to 0 minus 1 cubed, which is going to give me negative 1. So I do know that I have this critical point at 0, negative 1. I'm going to do the same thing for my x-intercept. Except when I'm finding my x-intercept, obviously I'm not making x 0, I'm making y 0. So I'm going to get 0 equals x squared minus 1 cubed. I'm going to take the cube root of both sides. So 0 equals x squared minus 1. I'll bring that 1 over. And then I'm going to take the square root of both sides, and I'm going to be left with x is equal to plus or minus 1. Now this leaves me with two critical points here, 1, 0 and negative 1, 0. Notice how I've just been boxing all of these off, whether you want to highlight it, whatever you want to do, just so that you're not searching all of your pages for those critical points again. All right, now that we've found our intercepts, we are going to be talking about our critical points. Now again, these happen when our derivative is equal to 0. So I'm going to find my derivative, 3 times x squared minus 1 to the power of 2 multiplied by the derivative of that inside. Now I can simplify this a little bit. I have two monomials here, so I'm just going to combine them. So 6x times x squared minus 1 squared. If I set this equal to 0, I am able to find those critical points. So I've got one at 0, and then I have another at x squared minus 1 equals 0, x squared equals 1, x is equal to plus or minus 1. So again, I'm just going to write these a little bit nicer. I do have this important point at x equals 0, and then again at x equals plus or minus 1. Now what you might notice is that some of these points are overlapping. I know that when x is plus or minus 1, that is my x-intercept. That won't always happen, but in this case it does, and that's okay. Okay, so what I have here is our table. So I left a spot for our test value, f prime of x and f of x. I've put in all of those critical points, so the negative 1, the 0, and the 1 with the intervals that are before and after those points. I'm going to go ahead and pick some test values right now. Obviously, these ones are going to be the same. I'm going to pick something less than negative 1. I'm going to pick something between negative 1 and 0, something between 0 and 1, and something greater than 1. So I've just added in the derivative and the original function so that I don't have to keep flipping back and forth. You probably have them on your own notes, so that's okay. I'm going to go ahead and plug in this information. So again, for my critical points, I know that the derivative is always going to equal 0, so those are easy. When I look at this derivative, I know that this entire bracket is squared. So regardless of what I plug into that bracket, it's going to be a positive result. So really, I only need to focus on this part of the derivative. So if I plug in a -2, this is going to be negative. Again, I don't care about the number. I only care about whether it's positive or negative. If I plug in -1/2, this will also be negative. +1/2 will be positive, and a +2 will be positive. Now I can go ahead and think about what this means in terms of our original function. If the derivative is negative, I know that my function is decreasing. At 0, it's horizontal. Again, it's decreasing, horizontal. Now my derivative is positive, so it's increasing, horizontal, and then increasing. So these arrows really are helping us figure out what's going on in this graph. I notice here that I have a decreasing to a 0 to an increasing, so that's going to represent a local min. And then here I see that I have a decreasing with a decreasing, and then an increasing with an increasing, and hopefully you recognize that those are going to be some points of inflection. So now that we have all of this information, we can start sketching our graph. So the first thing that we're going to do when we sketch our graph is we're going to plug in those x-intercepts and y-intercepts along with our critical points. Now in this example, we know that they're already kind of doubling up. Some of them are the same, and that's okay. So I do have a y-intercept of -1. I've got those x-intercepts of +1 and -1. Now those are also the same as my critical points. Now you'll notice that I wrote up here as well, we recognize that this was a degree 6, and since it was even, it was going to go from quad 2 to quad 1, even and positive, I should say. So we know that it's going to be starting up here. It's going to hit this critical point, and we know that because it's a degree 6, and because of the way that our arrows are going, it's going to flatten out a little bit, and then it's going to start heading back up like this into quad 1. I am going to attach an actual Desmos picture just so that you could see exactly what's happening, because this sketch is very rough, and then we will start talking about concavity. Alright, so I've put this Desmo graph in here, and it's definitely a lot nicer than mine, and it's very easy to see the points of inflection here at -1 and +1, and so I'm just going to try and go through. I'll use red. What we can tell from the chart is that it is a decreasing function followed by another decreasing function. Now, we know that if we have that decreasing to decreasing or increasing to increasing, that represents a point of inflection. We also said that it happens when something changes from concave up to concave down, or concave down to concave up. So what I have here is this, which is half of a U shape. So that represents a concave up function. And then it gets to this horizontal spot, and then it changes to half of this N shape, or a concave down. Now at that point where it changes, that is my point of inflection. And the exact same thing happens here. So we have a concave down, and then it switches to this concave up. So I just really wanted to put this Desmos graph in there. It's a lot easier to see, and of course we are going to be talking about concavity more in the next little bit of this video. So example 2 says the graph of y equals x cubed has a point of inflection at x equals 0. We've already talked about this. Graph this function and its derivative to examine what happens before and after x equals 0. So we're going to call this first key point, so this -2, 8, we're going to call it A. I'm going to call this second key point B, and I'm going to call this one C. So based on prior knowledge, we can see that this function is increasing from A to B, and it is also increasing from B to C, but there's a major difference in the way that they're increasing. So basically what we have, it says, I'm looking right here now, the slope from the slope of the function from A to B goes from a steeper slope to a more gentle slope. if I picture these tangents being drawn in, my tangents are very, very steep. And then the closer that I get to B, the less steep that I get. They're still positive, they're just a gentler slope. This represents something that is concave down. Now again, if you think about what's happening, this looks like half of this upside down U shape or this N shape. The exact opposite thing happens from point B to point C. So it's still increasing, it's still positive, all of my slopes are positive, but they're starting off not so positive, and as I go further, they get more positive. This represents something that is concave up. And if you want to think about this, this would represent half of a U shape. And so you really want to make sure that you have a good understanding of those differences as we move forward and that you're not getting those switched in your head. I know it's very easy to do, especially for me when I'm talking. I probably have mistaked them in past videos, but you do have to just be very careful with what you're saying. The next part of this question asks us to take a look at its derivative to examine what's happening before and after x equals 0. So when we look at this graph, we know there's something happening at x equals 0. We're going to actually figure out our critical points. So we're going to take the derivative of this function, so 3x squared. We're going to set that equal to 0, and yes, you have seen me do this. And this is going to give us a critical point of x equals 0. This is what we wanted, but now what we're going to do is we're going to take this derivative again. So now I'm going to go ahead and I'm going to do this double derivative. So y double prime is equal to 6x, and when I set that equal to 0, I get an x of 0, which is the exact same. So what this represents, or what this double derivative represents, is a point of inflection. So sometimes our critical points aren't going to be a maximum or a minimum. Sometimes they are going to be a point of inflection like we see with this cubic function. So now I've taken this interval chart and I'm kind of expanding on it. So now I don't have my derivative in my original function. I have my derivative and my double derivative. So our only critical point was 0, and we know that if we plug that into our double derivative, we get 0 as well. I'm going to choose a test value of -1, something less than 0, and then something greater than 0, I'll choose a test value of 1. So if I plug in -1 into my first derivative, I get 3 times -1 squared. That's going to give me a positive result. If I plug that into my second derivative, I get 6 times -1, which is a negative result. I'm going to do the exact same thing with my interval x is greater than 0. So if I plug in a +1, I get, again, a positive result. And if I plug a +1 into my second derivative, I get a positive result. This tells us, this double derivative information tells us if we see a negative, that means that we have something that's concave down. And if we see a positive, that's a concave up. I am going to continue on with some more examples, but it will have to be in part B of this note.